The Dirichlet theorem not only tells you that you can approximate an irrational number with a rational number, and it also tells you that its approximation by rational numbers can be very fast. Now, given this Dirichlet theorem, let's make another observation. If we multiply both sides of this by q squared, or we multiply the both sides of this by qn squared, you will get q squared times this absolute value is bounded by 1. And this left hand side can be written as q times the absolute value of qu minus p. And here we assumed without loss of generality that q is positive. Otherwise, you just change the sign of the numerator p. And now what is this? This guy is bounded below by q times the decimal part of this guy is bounded below by q times the decimal part of q times u, because p here is an integer. So this absolute value is always greater or equal to the decimal part of q times u. So here this notation means qu minus the integer part of qu. And furthermore, this part can be further bounded below by this. This guy is greater or equal to q times the decimal part of qu. And the decimal part of qu, so here this notation means qu minus the floor of qu, which is the decimal part of qu. And this guy can be further bounded below by this, by q times the distance from qu to the integer closer to it. The minimum of qu minus p, where p ranges in the set of integers. And what the Dirichlet theorem or this result tells you is that if you accept the fact that every irrational number u has a continuous fraction expansion, then for any real number u, there is a sequence q sub n with q sub n goes to infinity as n goes to infinity, such that q sub n times the distance from q sub n times u to its nearest integer is bounded by 1. And I said this is true for any real number u. When u is a rational number, this is trivially true, because in that case you just take q sub n to be the decimal part of u, and this guy will become 0. I mentioned this here because there's a very big deal related to this result. Now here's the question. If you consider the product n times the distance from n times u to its closest integer times the distance from n times v to its closest integer, and you take the lim_inf of this as n goes to infinity. And what do you get? So from here, you may want to guess that this lim_inf might be equal to 0, because this part is already smaller than 1, and this is smaller than 1. So you may want to guess that this is probably equal to 0 for any real numbers u and v. And I told you that this is a big deal because this is not just any question. This is a conjecture due to Litterwood in 1930s. Many mathematicians have investigated this conjecture over the decades. There are a lot of big names. And unfortunately, maybe I should say fortunately, this conjecture still remains open today, so that mathematicians still have some work to do. Although there are a lot of results related to this conjecture, let me just mention one result that I care about. This is a theorem due to the following three very famous mathematicians. The first one is the author of this book we are using now, Seidler. The second one is Katok, and third one is Lindenstrauss. He's a Fields medalist in 2010. And the year, I think, is 2003. They use the ergodic theory methods to prove that the pairs UV that fails the Litterwood conjecture is extremely small. Specifically, they prove the following. Let theta be the subset of R2, consider the pairs UV where the lim_inf as n goes to infinity of this product of three things is strictly greater than 0, then this set has Hausdorff dimension 0. You probably don't know the meaning of Hausdorff dimension, but let me just tell you, if a set has Hausdorff dimension 0, then it is very, very, very small. So informally, this tells you that theta is very small. Because there are sets of Lebesgue measure 0, which has positive Hausdorff dimension. And if a set has Hausdorff dimension 0, then it has to be very, very small. And let me briefly mention that their proof relies on a partial classification of certain invariant measures on this homogeneous space SL3R mod SL3Z. This is a space of radical sets of SL3Z in SL3R. And now let me give you some feeling how hard the Litterwood's conjecture is. As I said earlier, that the proof of the Litterwood's conjecture can be boiled down to the classification of certain invariant measures. Now if you consider the actions of the group A of positive diagonal matrices in SLKR for k greater or equal to 3 on the space SLKR mod SLKZ for k greater or equal to 3, if you consider those actions. And now consider this measure. If mu is an A invariant ergodic probability measure on this space, is there a closed connected group L above A for which mu is the unique L invariant measure on a single closed L orbit. We call this phenomenon the measured rigidity for mu. If this is indeed satisfied, then we call that mu is homogeneous. So, the proof of the Litterwood's conjecture boils down the classification of those homogeneous measures. And what those three mathematicians, Anselder, Katok, and Lindenstrauss, answered this question under the additional hypothesis that the measure mu gives positive entropy to some one-parameter subgroup of A. And this partial answer to this question is used to show that the set of exceptional points for the Litterwood's conjecture is extremely small, namely having Hausdorff dimension 0. And if you can answer this question without additional hypothesis on the measure mu, then you will give the full answer to the Litterwood's conjecture. That roughly gives you some idea how hard this conjecture is. And this is very unlikely to be something you can prove with just the real analysis in the undergraduate level.